Okay, so an optimization problem with some context finally, not just like, two numbers. We're actually trying to maximize something with context. So it says a farmer has 120 feet of fencing with which to enclose two adjacent rectangular pens as shown. What dimensions should be used so that the enclosed area will be a maximum? So we are trying to maximize the area, right? So when we write our statement for area, this is what we're going to be maximizing. And then they also want to know in this case what will be that maximum area. So let's not forget about that as we get going. So the area of this shape, I mean, you could express it a couple different ways. You could say, that this is half y and that you have two of these, but obviously the simplest way to express the area of this entire pen is just xy. But how do we maximize that? Okay. Maximizing to find the max or min when we're in calculus. And if you're watching this video and you're not in a calculus class, this might not make the most sense. But if we differentiate this and find the critical points by setting it equal to 0, that will tell us where the maximum occurs. Again, do we want to differentiate this statement? Do we want to use implicit differentiation? Not if we can avoid it, right? Nobody likes that. So how do we do that? We set this up as a system, okay? And that system implies that there would be two equations that we can work with and do some substitution and whatnot. So when it says a farmer has 120 feet of fencing, let's use that. Well, that 120 feet of fencing has to account for all of the sides of this pen. So we have 3 sides of length x and 2 sides of length y. So that means 2y plus 3x has to equal 120. So again, the idea is to write this area statement only in terms of x and then differentiate with respect to x. So to do that, I need to solve for y in terms of x over here. So if I do that, I would get y equals 60 minus 3 halves x. I'm not going to use decimals. You could use decimals, whatever your preference, I suppose. But so now I'm going to take this value of y. I'm going to close this off here. And I'm going to say that the area now is x times 60 minus 3 halves x. That's my y value. Okay. So I'm a fan of, if at all possible, right, before we try to differentiate this, because look, can you use the product rule to differentiate this statement? Yes, you could, but you could also make it a heck of a lot easier by writing it as a polynomial, and then we only have to use the power rule. Okay, so that would be my advice. Try to write that as a polynomial. The only time you can't really do that is if you have x in the denominator, or if you have a quantity raised to some power, like a half power or something like that. We've seen those on some of the other videos. But in this statement, I can actually multiply these and get that polynomial version of that statement. Now, if I differentiate this with respect to x, I get 60 minus 3x. That worked out nicely, right? So 60 here, take the 2, multiply it times 3 halves. These 2's will cancel, so we have 3x. Subtract 1 from there, you get 1. So this is the derivative of the area statement. How do I maximize the area? I take the derivative and I set it equal to 0 and solve for the critical points. So subtract 60, divide by -3, we're going to get x equals 20. So again, that x, that is this. Okay, that's the statement that we wrote for the area. So we know what this value is. This is 20, this is 20, and this is 20. Right? What's y? Well, take that value of x and plug it in over here. Y would equal this 60 minus 3 halves of 20, which is 30. So now we have our dimensions, because again, this y is this y. So now we know that's 30. And then the max area, okay, the area is 20 times 30. We don't have to go back and use that original equation. How do you find the area of a rectangle? 20 times 30, so that's equal to 600. I believe it was square feet. There you go. So max area determined by these dimensions of the rectangle, which were found by setting the derivative equal to 0. Ooh, saved by the bell.